methods in civil engineering, we will continue with our discussion on solving nonlinear multidimensional nonlinear equations. In our discussion last time, I tried to drive home the point that the solution of nonlinear equations is best, multidimensional nonlinear equations in particular, is best understood in a particular physical context, right. If you look at a particular equation and look at a particular context in which that equation arises, it is much easier to understand it than understanding it in the abstract. And we decided to look at the response of a structure which is in equilibrium, the nonlinear response of a structure which is in equilibrium due to the action of applied loads, right. And we said that the nonlinearity might be of because of any reason, maybe because of geometric nonlinearity or maybe because of material nonlinearity. So, basically the problem becomes that we have to solve this nonlinear equation and we have to solve it incrementally. So, we have to decide what is driving the solution, what is my input and what is my output. The input in this case we decided is going to be our load vector, right. So, we are going to increase the load step by step, and then at every step we are going to iterate. Since it is a nonlinear problem, we have to iterate until we find a displacement solution which results in an internal force which exactly equilibrates the external force. And once it equilibrates, we are converged for that increment. We move to the next increment, again we increase the load, and then we again iterate until we reach equilibrium, right. So, basically knowing Pn plus 1, we have to find Un plus 1 such that they belong to the set of solutions of my nonlinear equation f, which is a function of u and p, where u and p are vectors, right. For the purpose of understanding, it often helps if we consider a two-dimensional idealized schematic of the problem. This is just a schematic just to help your understanding. It is not at all a representation of the reality, where the load vector p and the displacement vector u are treated as single scalars purely for illustrative purposes, right. And then we have this blue dot, which represents a equilibrated state where we know the load Pn, we know the displaced configuration which results in equilibrium, right. And then we decide to increase the load from Pn to Pn plus 1, and we want to find the displaced configuration Un plus 1 which results in equilibrium. So, we want to find this blue spot, right, which is my next equilibrated state. But to go from here to here is not easy, you can see, because this slope is not a constant, right, this slope is varying. So, if I take an initial step based on the slope here, I am not going to reach equilibrium. I have to iterate till I go back to and hit a point on the red curve. And the red curve, as I said last time, represents the response of the structure to the applied load. It can be thought of as representing the internal force vector g of u, right, internal force vector g, which is again a function of my displaced configuration u. At equilibrium, the internal force must be equal to the external force, that is g of u must be equal to p, which is simply a modified version of my original equation f of u p equal to 0. So, this was my original equation, I am now rewriting it as g of u equal to p, right. And then we want to, instead of solving this equation, I am going to try to solve this equation in an iterative fashion, and if we do, we get a sequence of nonlinear equations of the form g of un is equal to f of n is equal to 0, 1 and so on for each load step. So, given un and fn such that g of un is equal to fn, which corresponds to a lone equilibrated state, and knowing fn plus 1, we want to find un plus 1 such that g of un plus 1 is equal to fn plus 1. So, to do that, we have to start with an initial guess, right. So, we have to assume that some value for my displacement increment, right. So, starting from here, right, I assume some value for my displacement. How do I assume that value? How do I find that value? Well, I use the tangent here. So, let us see how we do that. So, you start with an initial guess for u tilde n plus 1, and given that initial guess, we compute the internal force again, g u tilde n plus 1, right. So, I compute an initial guess for my updated configuration, put my updated configuration in my equations which generate the internal force. I do not want to go into the details of those equations. Let us assume that they are known, right. I have some equations where I put in a certain displacement value, I get back an internal force. Let us treat that as a black box, right. So, we get back the internal force, but that internal force is not going to be equal to my external force because of the nonlinearity, because the slope because my u tilde n plus 1 is not really my converged value, and that is going to result in a disequilibrium, in a difference between the external and the internal force, right. And that difference f n plus 1 minus g u tilde n plus 1 is denoted as the residual. It is the residual vector r n plus 1, and the purpose of my iterative scheme is to change u n plus 1, change u tilde n plus 1, so that my residual goes to 0, right. So, that my residual is minimized. So, the purpose of the iterative scheme is to minimize the residual vector r n plus 1. So, what is the physical meaning of the residual vector? Well, the residual vector is nothing but the part of the load that is not balanced by the internal forces, right. It is the out of balance force. Okay, so that is how we go about it. So, let us take a step back again. How do we compute the trial solution u tilde n plus 1, or in the usual nomenclature of iterative schemes, how do we compute the increment delta u tilde n? So, I am just introducing some new terminology. I am saying that u tilde n plus 1, the change in the value of u, right, u tilde n, that is it is the guess u tilde. Why do I have a tilde? Because that is my guess to the displacement at n plus 1, right. My guess minus the value of the displacement at step n is the approximate increment in u tilde n. When this becomes exact, the tilde will go away, right. So, then I will have del u n is equal to u n plus 1 minus u n, but since it is approximate, I have the tilde. So, given that u n, we know u n and f n, as well as delta f n, which is equal to f n plus 1 minus f n. So, this is known, the increment in the load is known. So, we will use a generalized form of the Newton-Raphson algorithm for the update, and according to Newton-Raphson, recall what is the Newton-Raphson algorithm all about? It is about linearizing that nonlinear equation about a given solution. I have a certain solution, I know u n f n, right. I approximate my true solution by assuming that the true solution is a straight line, right, with a slope which is given by the known tangent at u n f n, right. And then when that straight line intersects the x axis, the abscissa, that gives me my update, right. So, again, so I am using Newton-Raphson, I am saying this is my new iterate, right, g u tilde n plus 1, and since the ordinate is 0, it is the point where it intersects the abscissa. So, g of u tilde n plus 1 is equal to 0, and that is equal to g of u n, the starting value, plus the tangent times the increment, right. So, it is the starting value plus the tangent times the increment. So, from this equation I am going to get delta u tilde n, and delta u tilde n is nothing but g prime u n inverse g u n, right. So, it is just this. So, in mechanics nomenclature, g prime u n is the tangent stiffness at the solution point u n f n and is denoted as k n. Because of nonlinearity, delta u tilde n will not produce an equilibrated solution, and thus iterative condition corrections are necessary to eliminate the residual vector. So, my residual vector r n plus 1 is my new force, which is Fn plus delta Fn, right, Fn plus 1 minus G at u tilde n plus 1, which is Un plus delta u tilde m, right, and I have just represented this Un plus delta u tilde n as u tilde n plus 1. So this is my residual, right, this is my residual. I start with a guess and this is my residual, and then I have to minimize that residual. How am I going to minimize that residual? Again I will linearize. So let us again see what we do. So we iterate, we start with an iterating, and starting with an iteration counter I is equal to 0, we obtain the corrections by linearizing the residual about the ith estimate of the equilibrium state n plus 1 defined by Un plus 1 I Fn plus 1. So basically let us think of it like this. I have the residual at a certain iterate, right. Suppose I start with iteration 0, where for iteration 0 I have computed my del u tilde n like this, right, and that represents my iteration 0, and for that iteration 0 I have computed my residual like this, right. That residual is non-zero, right. So then I linearize the residual, right. So again I expand the residual in Taylor series about that iterate, right. I say that Rn plus 1 at I plus 1, at the I plus 1, I know everything at iterate I know the value of u at iterate I know the value of my internal force at iterate I know the value of my tangent at iterate I, right. So and then I want to find out what increment I must take in the displacement to make the residual smaller. That is my new problem, right. So to do that I expand the residual as a in Taylor series about the known state which is at iterate I. So I say that Rn plus 1 at iterate I plus 1 is equal to Rn at I plus the gradient at I times the change in the displacement increment, right. And I am saying that I assume that at, again this is like assumption is that at the new location, at the new displacement, at the new value of the iterate, my residual is 0, right. Similar, that is the same assumption everywhere for Newton-Raphson, right. So at the new iterate my residual is 0. So again that gives me the change, the increment in the displacement increment. It is like I computed some value of the displacement increment, now I have to change it at each iteration. So you can think of it as change in the increment or increment in the increment, whichever is convenient, right. So it is the change in the displacement increment delta u n plus 1, and to do that I move this to the right hand side, right, since this is known, right, everything at iteration I is known. I move it to the right hand side and then I invert this is a matrix, since this is a vector, this is a matrix, right. So I invert this and then I find out my new delta u I n plus 1, and once I find this I update, I say that knowing my increment at iteration I can find my increment at iteration n plus 1 using this sort of relationship, right. So we are going to continue doing this until what is the stoppage criteria? The stoppage criteria is that the residual becomes extremely small, right. When the residual becomes sufficiently small, I know that I can stop my iteration, but usually we use another stopping criteria. So I am going to talk about that. So we continue iterating this, we continue the iteration process until the residual becomes 0. Once the residual becomes near 0, equilibrium has been reached for load step n and new load increment is applied. So for that increment I have reached equilibrium, my internal force is equal to my external force, my residual is 0. The process of the residual becoming 0 is known as convergence, right. So this process is convergence, and the load increment is supposed to have converged when my residual that is the residual is a vector. So, I have to think of some sort of a scalar representation of a vector. Scalar representation of a vector means the norm of that vector, right. The norm of the residual vector is less than a small fraction of the applied load, right. So, if Fn plus 1 is my applied load and my residual has become a small, epsilon is a really small number, let us say 10 to the power minus 6 or 10 to the power minus 3, right. If it is 10 to the power minus 3, then the residual is 0.001 times my applied load. So, if my applied load is 5 kilonewton, my residual must be less than 5 Newton, right. So, when the residual is so small, I say that the residual is almost 0, I have converged, I can move on to the next increment. So, sometimes there is another criteria for the small residual criteria is supplemented by another criteria. What is that criteria? That criteria is that the change in the displacement. So, I am iterating, right. I have my initial guess del u tilde n plus 1, and at each at suppose 0, and then I compute I increment that at iteration 1, 2, 3, 4 and so on. So, at each increment I am adding something to my delta, right, and if I represent it by this, if I represent that quantity which I add by this, and I find that the change from iteration to iteration, my increment is changing by a really small number. And what do I mean by a really small number? I am saying that the norm of the change is 0.001 times the total change up till now. So, from increment 5, I suppose I know the solution at increment 5, I am interested in the solution at increment 6, and for that I have taken suppose 40 iterations. That is too big, but just for the timing let us assume that to go from increment 5 to increment 6, I have taken up till now 40 iterations, and my displacement increment to go from increment 5 to increment 6 is suppose 0.1 up till now, up to 40 iterations. Then at the 41st iteration, I find that displacement increment changes from 0.1 to 0.000001. So, it changes from 0.1 to 0.1000001. So, the change is really small. So, the change in the displacement increment is really small. So, that also tells me that the solution is converged, right. So, either the residual criteria or the change in the displacement increment criteria. This criteria implies that the correction in the displacement vector is negligible compared to the total magnitude of the incremental displacement vector. So, that is it. Now, let us take another a step back and recall that for 1D Newton iteration, we found that it may not be necessary to compute the derivative at each iteration. The resultant loss of accuracy will only marginally affect the rate of convergence. We saw that if the error in computing the actual function, the error computing the function value is more than the error in the derivative, then it is not really necessary to compute the derivative accurately, right, and we can save a lot of computational cost by not computing the derivative, by taking an approximation of the derivative. In multi dimensions, this is potentially extremely advantageous since the cost of computing the tangent stiffness is very high. You can see that if we perform an exact Newton iteration at exact Newton, then we have to compute not only the tangent matrix at each iteration, we have to invert it also, right. So, I said I was looking, I gave an example, right. Suppose I am moving from increment 5 to increment 6 and I have taken 40 increments. So, 40 iterations to move from 5 to 6. So, what does this mean? That means that each of those 40 iterations I have to evaluate my tangent stiffness. As soon as I get my internal force vector at the new iteration, I have to evaluate the tangent stiffness, and not only do I have to evaluate the tangent stiffness, I have to invert it, right. And in almost real world problems, I mean particularly problems which are common to industrial applications, the model is huge, right. So, matrices of size 100,000 by 100,000 are not uncommon, right. So, if I have to form a matrix of size 100,000 by 100,000, that is, it has a million terms, right, and then I have to invert that matrix 40 times to go from one increment to another, the computational cost is stupendous, right. So, in case instead of if instead of evaluating the tangent stiffness every iteration, if we can find an alternative, that would save the computational costs significantly. Moreover, at each iteration we need to invert the tangent stiffness matrix to obtain the update to the solution. Thus, if we can avoid having to compute the tangent stiffness at each iteration, we can save the cost of inverting it every iteration, provided we store the last inverted tangent stiffness. So, if I say that at a certain iteration I am not going to do my Newton iteration using my exact tangent stiffness, I am going to use a stored tangent stiffness. I computed the tangent stiffness in a previous iteration, and since I do not have to use the exact tangent, I am going to use that to solve my to calculate my increment, right. But then I probably need to store the inverse also, right. That is always better. If I store the inverse, I can directly use the inverse for do back substitution and calculate my update to the increment. For large systems, this can lead to huge savings, but unlike full Newton, it will not lead to quadratic convergence. Remember that we are only going to get quadratic convergence if we use the exact tangent, right. If we use the exact tangent at each iteration, then we are going to get quadratic convergence. But remember again, when do we get quadratic convergence? When we are in a neighborhood of the solution, right. When we are far away from the solution, we are not going to get quadratic convergence anyway, right. So, what is the harm? If we can use a less costly approximation to the tangent, then probably we are going to lose a little bit in our convergence, but as it is we are not getting quadratic convergence, but we are saving the computational cost a lot, right. And the idea of the modified Newton algorithm is to use an approximation to the tangent. So, the full Newton algorithm uses the full tangent. The modified Newton algorithm, which we are going to talk about next, uses an approximation to the tangent. The modified Newton method consists in moving the calculation of the tangent stiffness to outside the iteration loop. So, what do we mean by outside the iteration loop? Well, to put it in words very simply, it is this. We are saying that suppose I have my converged solution at increment 5. So, I know the solution at increment 5, I know u5, I know f5, right, and I know f6, I am interested in knowing u6. So, one way using full Newton is to compute the tangent at u5, right, compute the tangent at the known converged solution u5, then invert the tangent to get an approximate delta u tilde, to get an approximation to the update. That delta u tilde will probably not be the true solution, there will be a residual, there will be an internal force which will not match the external force. Go back and again I start iterating. So, starting with 0 iteration, I move to the next iteration. I again calculate the tangent there, I again calculate the update and move on. So, what does modified Newton do? Modified Newton says that okay, I will compute the tangent at the end of increment 5, but between increment 5 and increment 6 I am going to use the same tangent. So, between increment 5 and increment 6 we said that we need 40 iterations, right, we just made a guess, right. Suppose we need 40 iterations. Full Newton would say that each iteration, as soon as I compute that, as soon as I update, I am going to calculate the tangent, right. So, modified Newton says, well, no, I am not going to calculate the tangent at each of those iterations. I am going to calculate the tangent at a converged solution at the start of the increment, and then I am going to store that tangent, store the inverse, and then use that for all the intermediate iterations between 5 and 6. I am going to use the same tangent to compute my update. So, that's what it means by saying that I am going to move the calculation of the tangent stiffness to outside the iteration loop. So, before I start iterating, I compute my tangent, but within the iteration loop my tangent does not change, it remains constant, right. So, then kn at iteration I is equal to k minus 1 for all I, right. It remains at the value at the end of the previous converged increment, right. So, kn I for all iterations I is equal to kn minus 1, that is the tangent stiffness is only computed and factored. What do I mean by factored? Well, we looked at all those factorization schemes, Gauss elimination, LU decompositions, all those factorization schemes which help in inverting my matrix, right. So, I am going to keep those factors only once. I basically what I mean to say in simple words is that I am going to store the inverse only once for each load step on the basis of the previous converged state of displacements, right. So, kn I for each iteration I, this is going to be dr un minus 1 du. It is going to be the derivative of the residual, with residual is nothing but you can think of this as the internal force, right, with respect to u, right. In contrast, if full Newton iterations are used, then kn I is equal to dr u n I du. So, it is at each iterate I am taking the derivative to compute my new tangent, right. So, that is my modified Newton. Another way to think of modified Newton is that it preserves the tangent stiffness that is computed during the initial iteration of any load increment and uses it for all the iterations during that increment. However, during the iteration, as soon as the displacement update has been determined, the corresponding internal forces can be evaluated. So, remember, we are computing the displacement increment. At each increment, at each iteration, we are updating the displacement, we are calculating the internal force. Only thing that we are not doing in modified Newton is that we are not calculating the tangent, right. So, that is modified Newton. So, people came up with the idea that, well, we are computing the internal force at that increment at each iteration, right. Can we use that internal force computation to do some simple modifications to the tangent stiffness which I calculated at the beginning of the increment? I am not going to compute the whole tangent stiffness at each iteration, but I am going to use my original tangent stiffness and perform some little changes, right, some simple changes, some little updates which will not require inverting a whole matrix again, right. Can I make some small changes to my tangent stiffness because I have some updated information, I have some new information. At each iteration I have got the new internal force, right. So, will the new internal force that I am calculating at each iteration, can I use that information to update my tangent stiffness to get a better estimate of the tangent stiffness without actually computing the full tangent stiffness? Well, so that becomes the basis of what is known as the quasi-Newton method, right. So, up till now we were looking at modified Newton, now we are thinking of quasi-Newton. Modified Newton just uses the old tangent and continues it for all the iterations within an increment. Quasi-Newton, it keeps the old tangent and then it tries to make small stepwise modifications to that old tangent using the information, the updated information of my structure of my response, which is given by the updated internal force, right. So, this information, so this internal force, this updated internal force modification, the information can be used to construct modifications to the tangent stiffness to yield improved convergence properties with modest computational effort. Remember that as soon as we use modified Newton, we are going to take a hit in terms of convergence. Our convergence is not going to be as good. So, now the idea is that if we try to improve my stiffness matrix marginally at each iteration, maybe I am going to get better convergence, right. So, that is the idea. Basically, we attempt to use a secant relation of this form. So, I think that is better explained by this little picture here. So, suppose this is my converged state. So, this is my force, right, and that is my displacement at a certain converged state. So, I have to go from here to the next converged state, right. So, what I do is that I go from here to here. Suppose I have gone from here to here using a number of iterations, right, and then, or let us suppose in one iteration itself, right. So, I have gone from here to here in one iteration, right. So, that results in a change in displacement delta u and a change in the internal force delta g, right. So, then I construct a secant stiffness. What is a secant stiffness? It is delta g by delta u, right. So, that gives me an approximation to the stiffness, and I use this secant stiffness to update my tangent. So, to find the tangent here, to find that, if I use full Newton, what would I do? I would go ahead and find the tangent here, right. I would find the tangent here, but I do not do that. I say that I am going to keep my original tangent, but I am going to modify it. And how am I going to modify it? Well, I am going to modify it using the information on my secant, right. So, this was my original slope. This was my think of it, if we think of it in terms of slope of this line, this was my slope at the converged solution. This is probably the slope, a line probably something like this is the slope at the new iteration, but I do not want to evaluate that, that is too expensive. So, I say that I will use this original tangent plus the information about the secant, because I have to compute the update in the internal force. I know the update to the displacement. So, using this and this, I am going to get a secant stiffness, and using this secant stiffness, I am going to construct an approximate tangent here, right. So, I am going to construct an approximation to the tangent here using my original stiffness plus the slope of this secant, right. So, that is the basic idea of the quasi-Newton iterations, right. So, basically we attempt to use a secant relation of the form k delta u is equal to delta g. Knowing the update delta u, the increment to the internal force delta g is evaluated. Then an approximate to the secant k is constructed to update the already known matrix k0, right, to update the already known matrix k0. So, corrections to the stiffness matrix k0 are introduced in the form of the vectors delta u and delta g. These are the things that I know, right, delta u and delta g. So, if I have to construct corrections to k0, I have to use those known information. The most popular update formula is a symmetric rank 2 correction, the so called Broyden, Fletcher, Goldfarb, Shano update, which is popularly known as the BFGS update, right. Why is it a rank 2 correction? Well, you can see it from here. This is my original stiffness, and these are the changes that I am making to the original stiffness to obtain my updated quasi-Newton stiffness. Each of these updates is a rank 1 matrix. Why is it a rank 1 matrix? Because it has got only one independent row or column, right. So, it is the cross product, basically if you think of it like, not the cross product, sorry, it is the tensor product of this vector k0 delta u with itself, scaled by this quantity at the bottom, which is a scalar, right. Delta u transpose k0 delta u is nothing but a scalar, and this is an outer product, right. It is a tensor product. K0 delta u is a vector, that vector outer product with that vector itself, right. Since it is the outer product with itself, it is a rank 1 update, right. There is only one independent vector. So, that matrix has got only rank 1, right. So, that is a one rank 1 update plus another rank 1 update. So, it is a rank 2 correction, right, rank 1 plus rank 2, one rank 1 plus another rank 1. So, what it basically does is that it removes the stiffness K0 in the direction delta u and replaces it by an outer product of delta g. So, you can see what it does. It takes the original stiffness, right, then it takes the projection of that original stiffness in the direction of my displacement update K0 delta u. It is projecting the original stiffness, and if you think of it in very simply in terms of vectors, right, it is taking that original stiffness and projecting it in terms of in the delta u direction, and that part it is removing from the original stiffness because there is a negative sign, right. So, that part it removes from the original stiffness and it adds another part which is nothing but the outer product of my increment in the internal force vector, right. So, it projects out the stiffness in the direction of the displacement increment and it adds a stiffness, it replaces it, I would say replaces it by this term delta g transpose. So, in directions orthogonal to delta u, no change in the stiffness is introduced. So, basically in the direction delta u, it projects out something and it adds something. So, in directions orthogonal to delta u, there are no changes. Now, why does this update formula work? Well, one might ask, well, you are changing your original stiffness. This was your original stiffness. You are changing by this, you are performing a rank 2 update. So, your new stiffness, your new tangent stiffness is going to have a totally different inverse, right. The inverse of my new updated tangent stiffness after my quasi-Newton update is going to be totally different from K0. So, then in that case what is the advantage? Since the new tangent stiffness is totally different from my K0, do not I have to factorize it? Do not I have to invert it again? So, it's the cost is going to be exactly the same. In n square matrix I have to again invert that n square matrix. So, where is the saving? Well, the saving is because of this very important formula which is known as the Sherman Morrison formula. The Sherman Morrison formula says, if you look at it, it says that if I have an original matrix A and then if I construct a rank, if I update it like this, right, basically I update it like this, A tensor product B by H, I update it like this, then the inverse of my updated matrix can be written in terms of the inverse of my original matrix. So, what is the advantage? Then I do not have to convert, I do not have to invert this n by n matrix, new n by n matrix anymore. I can use my old inverse and then operate on that old inverse on that vector. That is just a matrix vector multiplication, which is much cheaper than inverting a matrix. Another matrix vector multiplication, which is again very cheap. So, matrix vector multiplication, when I get two vectors, this vector and this vector, with these two vectors I construct an outer product, I scale it with this scalar, right, and that is my new inverse. So, this is exact, this formula, this Sherman Morrison formula, is exact. So, it says that given a matrix A and in case I change that matrix like this, then I do not have to invert that whole matrix again. I can construct the exact inverse of the new matrix by just taking the old inverse and operating with that on a vector and then taking the outer product, right. So, that is why this whole thing works, otherwise there would be no point, right. If after getting this new tangent stiffness, if I have got to invert that whole n by n matrix again, then this quasi-Newton update is no good at all, right. So, the quasi-Newton update works because of the Sherman Morrison formula, right, which says that if you have a rank 1 update, you do not really need to invert the whole matrix, the new matrix, to find out its inverse. Well, you can use the inverse prior to the rank 1 update to find the new inverse in a simple and cheap fashion, right. Okay, so the BF, so that is the Sherman Morrison formula. the BFGS update, basically this update, right, we can regard it as two successive rank 1 updates. The outer product K0 delta u tensor product K0 delta u, that is this part, constitutes the first rank 1 update. I have already mentioned that, and the second part constitutes the second rank 1 update. So, with these two rank 1 updates, my new inverse is going to be, if I use my Sherman Morrison formula, right, if I use my Sherman Morrison formula and replace this A and B with my these vectors, right, with these vectors, then this is going to be my new updated quasi-Newton inverse, right. Is that clear? Right. So, this is the resultant inverse if I use the quasi-Newton update and then I use my Sherman Morrison formula, right. So, we can see that if we take, if we multiply this, if I operate with K inverse on delta G, then I am going to get back delta U, which shows that the update formula is a true secant update of the previous form. So, what am I saying? Basically, I am saying that this is my new updated matrix, right. So, if I operate on this matrix with my on delta G, the form is such, the structure of this matrix is such that if I take K inverse operating on delta G, I am going to get back delta U. And remember, that was our secant assumption, right. The entire secant assumption was this, that this is delta G by delta U, right. So, I have constructed my K inverse in such a manner that if I operate with that K inverse on delta G, and operate with K inverse, this K inverse on delta G, I am going to get back delta U, right. That is easy enough to prove using how the way outer products of the tensor products operate in vectors. It is, you can show that very easily. So, we are going to get back a true secant update of the form given in star. So, we can use this update formula every iteration, right. We start with my original converged solution, I evaluate the tangent, I take one iteration, I update it using my rank 1 update, right, using the BFGS update, right, and then I compute my new inverse using Sherman Morrison formula. Then I go to the next iteration. Again I have a new estimate of delta G, I have a new estimate of delta U. I use that to compute my update to my BFGS update again, and then I again use my Sherman Morrison formula, again construct the new inverse, right. So, this update formula can be used successively to modify the inverse of the stiffness matrix based on successive internal force and displacement sub increments. I am calling the sub increments, these iterations as sub increments, right. Now, in its original form, the BFGS method removes the stiffness associated with the specific displacement delta U and adds a rank 1 stiffness based on the force increment delta G. Let us go back and take a look again. So, it removes takes the projection direction delta U, removes it, adds the delta G. So, everything, all the changes to that K0 are occurring in the delta U direction, right. Thus, the stiffness change is related specifically to the directions delta U and delta G in the load space. Instead of using the BFGS update, there is another update form, another way of updating it. Well, what is the another update for another way of updating it? Basically, we change the stiffness, instead of only looking at delta in the direction delta U, we change the stiffness in all directions, right, in all directions. Alternatively, a general stiffness reduction beta for all finite displacement increments may be introduced by replacing K0 with beta K0. So, I had a K0, I am just going to scale it with a scalar beta, right, and a logical choice for the stiffness reduction factor beta would be delta G transpose delta U divided by delta U transpose K0 delta U. Why is that? Because delta U transpose K0 delta U is like the elastic work, right. K0 delta U, suppose that the material is elastic, which it is not, right, which may not be, right. I am not saying it is not, but it may not be, right. That K0 delta U times delta U transpose is like the elastic work, right. It is K0 delta U is like a force times displacement delta U, it is like the elastic work. If the material were elastic, this would be the elastic work, but the actual work is nothing but delta G transpose delta U, because the actual force is delta G, it is not K0 delta U, right, because the response is not linear, right. The delta G is no longer equal to K0 delta U. So, that force, the actual force moving through the displacement increment is the actual work, while the elastic force K0 delta U moving through the displacement increment is the elastic work. So, we say that the actual work is a fraction of the elastic work. So, we are going to change our stiffness by the same fraction. So, it is a beautiful idea, right, because the assumption is that I have K0, right, I have K0, and if I have that K0 constant, that represents an elastic matrix. So, the work done is K0 delta U times delta U transpose, but my actual tangent is not that. And what is the measure of my actual tangent? Measure of my actual tangent is the actual work done, right. If it were the elastic tangent, the total work done would be this. The actual work done is going to be delta G transpose delta U. So, if I take the ratio of these two, that is by how much I have to reduce my tangent from my elastic tangent, right. So, that is the idea, that is another way of doing the quasi-Newton iterations. Okay. So, that's all I had to say about various Newton iteration schemes, but the fact is that Newton iterations do not work in all situations, right, and they lead to divergence. The solutions do not converge under certain circumstances. What are those certain circumstances when the Newton iteration does not converge? Well, in many structural and solid mechanics problems, the load displacement curve changes slope. This typically occurs at limit points. At limit points, or for instance bifurcation points, right. For instance, when we have an instability in the solution, the slope becomes negative, right. So, if I draw my load displacement curve, the slope up till here, this load displacement curve had a positive slope. It reaches a limit point, the slope becomes 0, and then the slope has changed sign, right. In situations like this, the Newton-Raphson method cannot converge, right, because you can see why, because this tangent is predicting something like this, while the actual slope is like this, right. When this becomes too huge, it takes an increment like this, it goes somewhere here, and then it cannot find, there is no load displacement curve at that level, right. So, let us assume that it takes a slope like this, right, it takes a slope like this and it projects it out, right, takes a displacement increment, and then it tries to find a point on the load displacement curve to find the new equilibrium configuration, right. But the load displacement curve simply does not exist there, right, because it has changed slope, it has become totally different. So, it has a lot of difficulty in finding the new equilibrated solution, right. So, in such situations, typically we have problems, and this typically occurs at limit points, right, at load limit points. The equilibrium path following algorithm adopted so far moves from one equilibrium state to the next based on the tangent stiffness, right. If the slope undergoes large changes along the equilibrium path, it is necessary that the orientation of the path be correct and the step size along the path be controlled. Let us look at an example where you have a limit point, right, where the load displacement curve is changing slope here, it is changing slope here, right. So, suppose I went from here to here, right. So, this was my previous converged solution, I got another converged solution here, right, and then I construct my tangent. I construct my tangent to the converged solution, and it turns out that my tangent is like this, right. Its tangent is like this. This is my tangent. At this point I construct my tangent, and my tangent is like this, but this is pointing in the totally wrong direction, right. It's pointing in the exactly opposite direction in which the load display, in which my equilibrated solution lies. My equilibrated solution lies somewhere on this red curve, but if I compute the tangent here, and my tangent says that you take a projection, you take a step in that direction, that is the direction which is going to give you my slope, that is the slope at that point, right. Then I am going to go totally in the wrong direction, and I am going to get lost. I am not going to be able to converge anymore, right. So, in the right solution is actually checking the orientation. The orientation is this. So, the actual right orientation is that if I take a displacement increment in this direction, if I take a displacement increment in this direction, I will be totally lost. Once a limit point has been exceeded, there may be a need to change the direction of the load incrementation. What is another situation? Well, let us look at it like this. Here we have again we are looking at a maximum, right, where load has reached a maximum, my load displacement curve has reached a maximum, and then it is going down. Suppose I calculate the tangent here, right. I calculate a tangent here, and I take a load step like this. I have already mentioned this case, but I take a load step like delta u star, and then from here I try to find, for this delta u star, I try to find what is my internal force, but for this delta u star there is actually no internal force at all, because my load displacement curve is only up till here, right. So, there is no internal force at all. So, I am not going to get anywhere, right. So, what do I have to do? Well, in that case I have to cut back, I have to cut back on my displacement increment. So, what does that mean? That means that instead of taking my full delta u star, how did I calculate my delta u star? Well, I knew my tangent here, I knew my force increment here from here to here, I inverted that tangent matrix, I multiplied it by that force increment, that gave me delta u star, right. But if I take that delta u star, I am lost, because there is no internal force vector, this curve here. So, I have to cut back whatever estimate I got from my solution. I have got to reduce that increment, I have to scale it with this factor eta, right. The step size may need to be scaled. Instead of taking the full displacement increment delta u star obtained using delta u star is equal to k star inverse into delta f star, where delta f star is this little part, right, is this little part, and k star inverse is k star is the slope here, right, and then that is how I got delta u star. It may be necessary to scale the load and displacement increment in order to obtain convergence. Look at what I said. I said scale the load as well as the displacement increment, not just the displacement increment, also the load, and those are the basis of what are known as arc length methods. And we are going to talk about, we have various arc length methods, for instance the Rick's method and things like that, which are important for doing for any advanced finite element code. You will have these methods if they are interested in computing things like post buckling solution. I do not want to talk too much about solid mechanics or any particular application, but these are arc length methods are necessary when my when my solution curve encounters these limit points, which results in my Newton iteration failing, right. So, next class we are going to talk about arc length methods, and then we are going to talk about gradient methods, particular iterative methods which depend on calculating gradients, for instance the steepest descent method and the conjugate gradient method. Thank you.